Welcome back to the Explainer. So, if you've ever felt that mathematical concepts like perfect squares and cubic numbers or just, these abstract ideas confined to a whiteboard, you're absolutely in for a treat today. We are going to completely demystify the incredible properties of squares, roots, and cubes. And we're actually going to do it by solving a royal puzzle that relies entirely on uncovering these hidden mathematical patterns. All right, let's just jump right in. Starting off with Section 1, the 100 Lockers Puzzle. To really wrap our heads around this, let's set a scene straight out of a legend. We're talking about Queen Ratnamanjuri, her mysterious will, and her son Koisnam's quest to inherit her precious stones. The queen designed this absolutely brilliant setup to test her son's wit. Koisnam and 99 of his relatives are led by a minister into a secret room inside the mansion. In this room, there are exactly 100 lockers in a row, all initially closed. To claim the fortune, they have to follow a very specific synchronized set of rules. Okay, so here's how the game actually works. Each of the 100 people is assigned a number from 1 to 100. Person 1 goes through and opens every single locker. Then, person 2 toggles every second locker, so closing it if it's open, opening it if it's closed. Person 3 toggles every third locker. Person 4 toggles every fourth. And this massive relay basically continues until all 100 people have taken their turn. Now, the catch in the Queen's will states that only the open lockers will reveal the code to the safe containing the fortune. If they all figure it out, they split it. But if one person solves it first, they get the whole shebang. Incredibly, Koisnam figures it out before the physical toggling even begins, which leads us to our central question. How in the world did he know exactly which lockers would remain open? That brings us right to Section 2, Unlocking Perfect Squares. To understand Koisnam's stroke of genius, we literally have to look at the mathematical concept of factors. Every time a person touches a locker, it's because their assigned number is a factor of that locker's number. Take a regular number like 6. Its factors are 1, 2, 3, and 6. That's an even amount of factors, and they pair up perfectly. 1 pairs with 6, and 2 pairs with 3. Because locker 6 gets toggled 4 times, an even number of times, it ultimately ends up closed. But look at a number like 36. Its factors include 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6. Because 6 pairs with itself, 36 actually has an odd number of total factors. And that right there is the golden rule. Only perfect squares have an odd number of factors. Every non-square number has pairs of factors that toggle the locker an even number of times, leaving it shut. The perfect squares, however, get toggled an odd number of times, leaving their doors wide open. Koisnam knew instantly that lockers 1, 4, 9, 16, 25, and so on, all the way up to 100, would be the only ones left open. Oh, and as a really cool side note here, Koisnam was also asked to find a passcode from the first 5 lockers touched exactly twice. Think about that for a second. Touched exactly twice means a number only has the factors 1 and itself. He correctly identified these as the prime numbers, 2, 3, 5, 7, and 11. It's just a beautiful example of how deep mathematical truths are woven directly into this single riddle. Moving right along to Section 3, let's look at the actual patterns of these square numbers. Because they aren't just random, right? They follow some incredibly strict visual patterns. If we map out the squares of the first 10 natural numbers, an immediate pattern pops up right in the units place. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. Just notice the final digits for a second. You can literally see it. Perfect squares only ever end in 0, 1, 4, 5, 6, or 9. They absolutely never end in 2, 3, 7, or 8. This is a massive mental math shortcut you can use to instantly spot when a number is definitely not a perfect square. It saves so much time when you're estimating. Okay, prepare to have your mind blown just a bit by how we can geometrically build these perfect squares using simple addition. We're going to construct them using consecutive odd numbers, starting with the very first odd number, 1, which, of course, is just 1 squared. Now, just add the very next consecutive odd number to it. 1 plus 3 gives you 4. Geometrically, imagine taking a single block and wrapping 3 blocks around it. You've just built a 2 by 2 grid. 4 is 2 squared. And it just keeps going. Take that 4 and add the next consecutive odd number, which is 5. 1 plus 3 plus 5 equals 9. Wrap those 5 blocks around your 2x2 grid, and you instantly get a 3x3 grid. This brilliantly proves that every single perfect square is simply the sum of successive odd numbers starting right from 1.
All right, that's section 4, finding square roots and reverse engineering the whole process.
So we've spent a lot of time building perfect squares up, but what if we need to work backwards? Let's walk through this incredible mental math trick detailed in our source text to find the square root of 1936. First, you bound it. We know 40 squared is 1600 and 50 squared is 2500, so our answer has to be between 40 and 50. Second, check the last digit. 1936 ends in 6, so our root must end in either 4 or 6, leaving us with 44 or 46. Finally, just test the middle. 45 squared is 2025. Since 1936 is less than 2025, our answer has to be the smaller option. Boom, the square root of 1936 is 44. Which perfectly tees up section 5, stepping into cubes and hitting the third dimension. We've completely nailed the flat 2D area of squares, so let's add some depth. A cubic number simply expands our concept from a flat shape on a piece of paper into a solid 3D object where the length, width, and height are all perfectly equal. Mathematically, it's a number multiplied by itself, and then by itself again. N times n times n. Take a number like 64, for example. If you picture a physical cube with an edge length of 4 units, you're looking at 4 layers, each containing a 4x4 grid of 16 blocks. 4 times 4 times 4 means exactly 64 tiny unit cubes are packed perfectly together to create that larger solid cube. And that brings us to our final part, section 6, the famous taxicab number. To wrap up this explainer, we've got to talk about how cubic numbers played a role in one of the absolute best historical anecdotes in all of mathematics. The story goes that the brilliant Indian mathematician Srinivasa Ramanujan was recovering in a hospital when he was visited by his colleague, the famous British mathematician G.H. Hardy. Making small talk, Hardy mentioned that he had ridden in a taxicab with the number 1729. Hardy casually remarked that it seemed like a rather dull, uninteresting number and hoped it wasn't a bad omen. But Ramanujan, a guy whose brain essentially saw the numerical matrix of the universe in a way few ever have, he instantly corrected him. He delivered this legendary quote, "No, Hardy, it is a very interesting number. It is the smallest number that can be expressed as the sum of 2 cubes in 2 different ways." Ramanujan instantly saw the hidden 3D geometric beauty lurking inside a completely ordinary-looking license plate. Which leads me to a final challenge for you all. Can you find the 2 different ways Ramanujan was talking about? Grab a piece of paper, or just use mental math, and calculate the sum of 1 cubed plus 12 cubed, and then calculate 9 cubed plus 10 cubed. Work through those numbers, and you'll discover the magic of 1729 for yourself. Keep exploring, and I'll catch you on the next explainer.